we're doing some volume calculations today from chapter 18.1 and 18.2. I think you'll find these are pretty self-explanatory, nothing conceptually too difficult. We're just now working in three dimensions, hooray! So the first part is a couple different prisms. A prism here is defined as any shape just extended into that third dimension. So take a circle, extend it into the third dimension, we get a cylinder. If we get a rectangle extended into that third dimension, either up or down or left, right, whichever way, we essentially, like, think of a sheet of paper versus like a stack of papers, right? We now have a third dimension, height as opposed to, or depth as opposed to height or width, to deal with. So be prepared for that. It's relatively easy to find the volume of a prism. All you need to do is know the area of that base, so that main shape that you're extending. In this case, the base at the bottom. We'll just draw it at the bottom, and you multiply that by the height, that direction that your third dimension direction you're extending. So in this case, the area of the base with a big B times h. In this case, if we have a rectangular prism with length, width, and height, we just multiply them all together, right? Length and width and height, doesn't matter which order you multiply them in. That makes it extra easy if we happen to have, a perfect cube, right? Because a cube, the height and width and length are all the exact same value. So therefore, we take that value, multiply it by itself 3 times, and gives that value squared, or squared cubed, that value cubed, which makes sense because this is a cube, and that's why we use cubed for something to the third power. Cool. So again, the general formula for volume is the area of the base, right? In the case of this one, it's s squared times the height, again, times s equals s to the third. Okay, quick example. This one here has us find the area of this aquarium, which is 120 by 8 times 60. Multiply them all together, we get an answer. The book then has to try and make it harder because it can't be that easy. They want you to tax your brain a little bit. So then they want you to convert from gallons into from cubic feet into gallons. Again, you just multiply by their conversion factor here. Those of you who've done chemistry do this 10 times a day. Okay. Next, we're going to go back to like third graders playing with little cubes of units, right? So you have to figure out how many cubic units this is. Keep in mind that one of these little squares for problem 4 is 8 cubic units. One of the little squares for problem 5 here has a side length of 2k. So it's a little harder. See if you can figure out the volumes for both of these. I'll give you a second. Pause. Goodbye. And then we'll move this. This one here on the left, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 times 8 is 88, so this is 88 cubic units, whatever that is. This one's a little harder. 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 9 of these little cubes, and each cube has a side of 2k. So that means this is 2k, this is 2k, this is 2k. So the volume, right, is equal to 2 times k. We're going to cube that whole thing, right? So what is 2 times k times 2 times k times 2 times k? Well, that's 8k cubed. What is 9 times 8k cubed? It's 72k cubed. So I understand that that's a little difficult, but k here is just like a scale factor. Like think of it as a number. If you had plugged in 1 for k, this would be 72 cubic units, right? If you had plugged in 4 for k, it would be a huge number. Okay. Interestingly enough, it doesn't really matter if these things are slanted or not. Should have grabbed some. But you can think of an example of like a stack of pennies, right? If I have a stack of pennies and I were to just slant that stack off to the side, right? The height of that stack would be the exact same. It doesn't like dip lower or anything because I've slanted it. And the volume hasn't changed either. So keep in mind that the height of something may be independent of the side length, right? In this case, you can think of like the height of that stack of pennies, no matter how I slide it around, it stays the same. Even though this, right, I can measure that length up the side, that may become a bigger number. So the volume here is independent of this blue value, but it relies only on the height. So again, it's just the area of the base times the height. We can do, yep, same deal. The general volume formula is area of the base times height. That'll give us the volume for all these sorts of things. Right here, they're just looking at the plane. So they say, okay, if we just take a cross section and we slice it, again, just taking like a single penny out of the middle there, does it have the same shape? Yes. Does it go up the same height? Yes. So therefore, it doesn't really matter if it's scooting over or translating in the process. So here are a couple more. See if you can do these ones. I'll pause it again. Pause. Okay. This one, again, since the radius is 12, we're going to use pi r squared and then multiply that by 45. For this guy, we do 4x times 5x, right? Should give us 20x squared, and then we multiply that whole thing by this thing. This is good enough, really. I suppose you could distribute. You get 20x cubed plus 40x squared. I don't know why the book does it. Okay, so that's it for that guy. We'll move on to the next one real quick, since it's pretty similar to the volume of a pyramid, in this case, with the area B for the base, and the height h is 1/3 the area base times the height. And we are going to skip the proof for it, but just think, since we're going in a third dimension, as we shrink throughout that third dimension, we're just going to, it's going to be 1/3. So a little counterintuitive, because you look at this and you don't think like, oh, where's the 3 in here? But it's really just the fact that we're shrinking smaller in that third dimension. You can think of it that way. So our example here, feel free to read it. It's about the pyramid in Egypt. Remember, it's 1/3 the area of the base times the height. Well, what's the area of this base? This section here, right? That area is 230 times 230, which is some big number. And then finally, the volume of the whole thing is that big number times, well, the height times 1/3. So 1/3 times that thing times the height gives us a volume of this. And then they divide it out among the blocks. If you are curious about what the answers are there, I'll go ahead and give those to you. You can pause it if you want to write those down. Okay, see if you can do this one. Pause. Okay, this guy here, 2.5 times 1.5 is the area of our base, which is 3.75 square centimeters. And then to find the volume, we multiply that whole thing by 1.5 and 1/3. So essentially we're halving it, right? gives us 1.875. The units on that, though, should be centimeters cubed, cubic centimeters. And then finally, density, which we're going to do a separate lab on later, especially once it gets warm outside, is to just divide the mass by the volume, which gives us 19.7 over 1.875. Again, they have to put in that extra step because this stuff is just a little too easy for you to give us some number. Okay, that's it. That's all I got. Yeah, have a good day.